Welcome to this gentle exploration of the fascinating world of solar neutrinos. As we settle into this calming journey, we will drift into the depths of the universe to uncover the secrets of these elusive particles generated by the sun. Solar neutrinos are not only a crucial part of understanding the sun's inner workings, but also hold keys to broader cosmic mysteries. With soothing tones and a tranquil pace, we will explore their formation, detection, and significance in the universe. Let this serene journey guide you into a realm of knowledge and relaxation, where the wonders of science softly embrace you as you drift into peaceful slumber. In this first section, we will delve into the formation of solar neutrinos, understanding how they are created in the sun. The heart of the sun is an extraordinary place, a furnace of nuclear reactions where temperatures soar to millions of degrees. Within this core, hydrogen atoms fuse together in a process known as nuclear fusion. This remarkable reaction is the source of the sun's energy, and subsequently, the origin of solar neutrinos. The primary fusion process occurring in the sun is the proton-proton chain reaction. This chain reaction begins when two hydrogen nuclei, each consisting of a single proton, collide with sufficient energy to overcome their mutual repulsion. When they fuse, they form a deuterium nucleus, which contains one proton and one neutron, while releasing a positron and a neutrino. This initial step is critical, as it not only marks the birth of a neutrino, but also initiates a series of subsequent reactions that will ultimately produce helium from hydrogen. As the proton-proton chain continues, the deuterium nucleus can collide with another proton to create a helium-3 nucleus, which consists of two protons and one neutron. This reaction releases another neutrino, further contributing to the solar neutrino flux. Eventually, two helium-3 nuclei can collide to form helium-4, releasing two protons in the process. Throughout these reactions, neutrinos are produced and released into the solar environment, escaping the sun and traveling through space. The energy released in these reactions is immense. In fact, the sun produces an astonishing amount of energy, approximately 3.8 and 10 to the 26 watts, which is equivalent to the energy output of about 100 billion 1 megaton bombs every second. This energy is not only crucial for sustaining life on Earth, but also plays a significant role in the formation of neutrinos. The relationship between energy release and neutrino production is essential to our understanding of both solar physics and particle physics. In addition to the proton-proton chain, the sun also employs another fusion process known as the CNO cycle, which stands for carbon-nitrogen-oxygen cycle. While the proton-proton chain dominates in stars like our sun, the CNO cycle becomes more significant in larger stars. In this cycle, carbon, nitrogen, and oxygen act as catalysts to convert hydrogen into helium. The CNO cycle also produces neutrinos, although in smaller quantities compared to the proton-proton chain in the sun. The beauty of neutrinos lies in their elusive nature. They interact very weakly with matter, which allows them to escape the sun without being absorbed or scattered. This means that by the time they reach Earth, they have traveled vast distances, carrying information about the processes occurring deep within the sun. This property of neutrinos is what makes them unique messengers of solar activity, providing us with insights into the sun's inner workings that are otherwise difficult to observe. Neutrinos are not just passive observers, they also exhibit a fascinating phenomenon known as neutrino oscillation. Neutrino oscillation refers to the ability of neutrinos to change from one type or flavor to another as they travel through space. There are three flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. The transformation between these flavors is a result of the quantum mechanical properties of neutrinos and has profound implications for our understanding of particle physics. Neutrino oscillation was first proposed in the late 20th century when experiments began to detect fewer electron neutrinos than expected from the Sun. This discrepancy led scientists to hypothesize that some of the electron neutrinos were oscillating into muon, or tau neutrinos, which were not detectable by the original experiments. This realization not only resolved the so-called solar neutrino problem, but also provided evidence for the phenomenon of neutrino oscillation, which has become a cornerstone of modern particle physics. Understanding the formation of solar neutrinos is crucial as it lays the foundation for exploring their detection and significance in astrophysics. The study of solar neutrinos is not merely an academic exercise. It has profound implications for our understanding of the universe. As we continue on this journey, we will uncover how these elusive particles help us probe the Sun's inner processes and what they reveal about the fundamental laws of nature. As we reflect on the formation of solar neutrinos, we begin to appreciate their role as messengers of the Sun's energy generation. The complex interplay of nuclear reactions within the Sun's core leads to the production of these particles, which travel through space to reach us. Their existence offers a glimpse into the extraordinary processes that power our Sun and, by extension, our solar system. The journey of solar neutrinos from the core of the Sun to our detectors here on Earth is a testament to the remarkable interplay of forces at work in the universe. Each neutrino carries with it a story of fusion, energy release, and the fundamental interactions that govern the behavior of matter. As we drift deeper into the cosmic ocean of knowledge, let us hold on to the beauty of these particles, which, though nearly invisible, serve as a bridge connecting us to the very heart of our Sun. In the next section, we will explore the different types of solar neutrinos, delving into their characteristics and the nuances that distinguish them from one another. We will uncover how these differences affect their behavior and how they are detected, deepening our understanding of their role in the universe. For now, let the soothing knowledge of solar neutrinos' formation settle within you, like a gentle wave lapping against the shores of your mind as you drift towards restful sleep, cradled by the wonders of the cosmos. Thank you for joining me on this tranquil voyage into the science of solar neutrinos. As we delve deeper into the fascinating world of solar neutrinos, we transition into understanding the different types of these enigmatic particles. Solar neutrinos are not a single entity. Rather, they exist in various forms, each with unique characteristics and behaviors. This diversity among neutrinos is essential for our understanding of both solar processes and the fundamental physics governing the universe. The three primary types of neutrinos are electron neutrinos, muon neutrinos, and tau neutrinos. Each is associated with its corresponding charged lepton, the electron, muon, and tau particle. Electron neutrinos are produced predominantly during the nuclear fusion processes that occur in the Sun's core, particularly through the proton-proton chain reaction. This reaction is the primary source of energy for our Sun, and consequently, the most significant contributor to the solar neutrino flux that reaches Earth. Muon neutrinos, on the other hand, are generated through interactions involving muons, which are heavier cousins of electrons. These neutrinos are less prevalent in solar processes, but are produced in significant quantities in cosmic ray interactions in the atmosphere. Tau neutrinos are the least common of the three, and are produced in high-energy processes, such as those occurring in particle accelerators or supernovae. The rarity of tau neutrinos makes them particularly challenging to study and detect. The differences in mass and behavior among these neutrino types play a crucial role in their detection and the information they can provide. Electron neutrinos are the most easily detected because they are produced in the Sun and interact with matter more readily than their heavier counterparts. This interaction is essential for experiments designed to capture and study solar neutrinos, as these experiments rely on the ability of neutrinos to interact with other particles in a detectable way. Muon and tau neutrinos, due to their heavier masses, exhibit different behaviors in their interactions. They are less likely to interact with matter, making their detection far more challenging. This difference in interaction rates is a fundamental aspect of neutrino physics and has implications for their role in astrophysics. Understanding these types of neutrinos and their unique properties enhances our comprehension of the processes occurring both within the Sun and in the broader universe. Flavor is a key concept in neutrino physics, referring to the type of neutrino associated with its corresponding lepton. Each neutrino flavor can oscillate or change into another flavor as it travels through space. This phenomenon is known as neutrino oscillation and has profound implications for our understanding of neutrino mass and the fundamental forces of nature. The ability of neutrinos to change flavors suggests that they have mass, which was a surprising revelation in the field of particle physics. Neutrino oscillation occurs because neutrinos are produced as a mixture of different mass states. When neutrinos are generated in the Sun, they are predominantly in the electron neutrino state. However, as they travel toward Earth, they can oscillate into muon or tau neutrinos. This transformation is influenced by the differences in mass among the neutrino types and the quantum mechanical principles governing their behavior. The discovery of neutrino oscillation has opened up new avenues of research and has led to significant advancements in our understanding of particle physics. The methods used to detect solar neutrinos are finely tuned to exploit the properties of these particles. The early detection experiments primarily focused on capturing electron neutrinos, the predominant type produced in the Sun. One of the most notable experiments was the Homestake experiment, which utilized a large underground detector filled with a chlorine-based solution. When an electron neutrino interacted with a chlorine atom, it would produce a radioactive argon atom, allowing researchers to count the number of interactions and estimate the flux of solar neutrinos. As we moved into the late 20th century, advancements in technology led to more sophisticated detection methods. The Super Kamiokande experiment in Japan represented a significant leap forward in neutrino detection. This facility utilized a massive tank filled with ultra-pure water and surrounded by thousands of light sensors. When a neutrino interacted with the water, it produced a faint flash of light known as Cherenkov radiation, which could be detected by the sensors. This method allowed researchers to capture not only electron neutrinos, but also muon neutrinos, providing a more comprehensive picture of the solar neutrino flux. The Sudbury Neutrino Observatory, or SNO, further advanced the field by employing a unique method to detect all three types of neutrinos. Located in a mine in Canada, SNO used heavy water as its detection medium. This enabled the experiment to observe the interactions of electron neutrinos, as well as the conversion of muon and tau neutrinos into detectable signals. The ability to measure all three neutrino flavors was crucial in resolving the solar neutrino problem, a historical discrepancy between the predicted and observed rates of solar neutrino detections. The solar neutrino problem was a significant challenge for physicists. Initially, experiments detected only about 1/3 of the expected solar neutrinos, leading to questions about the Sun's energy production or the fundamental properties of neutrinos themselves. The resolution of this problem came with the understanding of neutrino oscillation. As researchers recognized that neutrinos could change flavors during their journey from the Sun to Earth, it became clear that the missing neutrinos were not absent, but were oscillating into different flavors that were not being detected by early experiments. This revelation had profound implications for both astrophysics and particle physics. The understanding of neutrino oscillation not only clarified the solar neutrino problem, but also provided evidence for the existence of neutrino mass, a concept that challenged the previously held belief that neutrinos were massless. The discovery of neutrino mass has since influenced the development of the standard model of particle physics, prompting scientists to explore new theories and frameworks to account for these findings. As we reflect on the role of solar neutrinos in astrophysics, we begin to appreciate their significance in understanding stellar processes. Solar neutrinos act as messengers from the sun's core, providing direct insights into the nuclear fusion processes that power our star. This information is invaluable for our understanding of stellar evolution, as it allows researchers to study the conditions and reactions occurring deep within stars. Moreover, solar neutrinos have implications for broader cosmic understanding. They contribute to our knowledge of the universe's fundamental forces and the interactions between matter and radiation. The study of solar neutrinos can shed light on phenomena such as supernovae, neutron stars, and the conditions present in the early universe. By examining the properties and behaviors of these elusive particles, scientists can piece together a more complete picture of the cosmos and the processes that govern it. In addition to their role in stellar processes, solar neutrinos also influence the development of theoretical frameworks in physics. The understanding of neutrinos has prompted researchers to explore new avenues in particle physics, leading to the development of beyond the standard model theories. These theories aim to explain the observed phenomena that cannot be accounted for by current models, such as dark matter and the matter-antimatter asymmetry in the universe. As we explore the cosmological significance of neutrinos, we find that they played a crucial role in the early universe. During the moments following the Big Bang, neutrinos were produced in vast quantities. Their interactions during this period influenced the formation of the universe as we know it today. Understanding neutrinos' roles in the early universe provides insights into the conditions that led to the formation of galaxies, stars, and planets. Furthermore, the interactions between neutrinos and dark matter are of great interest to researchers. Neutrinos are incredibly abundant in the universe, and their unique properties may hold the key to understanding the elusive nature of dark matter. Investigating how neutrinos interact with dark matter could reveal new insights into the composition of the universe and the forces that shape it. As we look to the future of solar neutrino research, we anticipate a new wave of experiments and theoretical advancements. Upcoming experiments aim to refine our understanding of neutrino properties and interactions, as well as to search for potential new types of neutrinos. These advancements will likely lead to many discoveries that will deepen our comprehension of the universe. One of the exciting prospects in this field is the development of next-generation neutrino detectors. These advanced technologies will enhance our sensitivity to neutrinos, allowing researchers to capture more data and explore previously uncharted territories. By collaborating across disciplines, scientists from various fields can contribute to a more comprehensive understanding of neutrinos and their implications for both particle physics and astrophysics. In conclusion, our exploration of the different types of solar neutrinos has revealed the complexity and significance of these particles in understanding the universe. From their formation in the Sun to their role in stellar processes and cosmic evolution, solar neutrinos are integral to our comprehension of fundamental physics. As we continue to investigate these elusive particles, we open the door to new discoveries that may reshape our understanding of the cosmos. The journey of solar neutrinos is a testament to the intricate dance of particles that weave the fabric of our universe, inviting us to ponder the mysteries that lie beyond our immediate perception. As you drift into a peaceful slumber, may the wonders of the universe gently cradle your thoughts, inspiring dreams filled with the beauty of science and the secrets it has yet to unveil. As we continue our exploration of solar neutrinos, we turn our attention to the intricate methods scientists have developed to detect these elusive particles. The detection of solar neutrinos is a remarkable achievement in the field of astrophysics and particle physics. It is a testament to human ingenuity and the relentless pursuit of knowledge about the universe. Understanding how solar neutrinos are detected provides us with insights into both their nature and the fundamental processes occurring within the Sun. The journey of neutrino detection began in the 20th century when theoretical predictions suggested that these particles should be produced in vast quantities during the nuclear fusion reactions in the Sun. However, the challenge was not merely in predicting their existence, but in capturing them. Neutrinos are incredibly lightweight and interact very weakly with matter, making them notoriously difficult to detect. In fact, they can pass through entire planets without any interaction. This property makes them unique messengers from the core of the Sun, carrying information about processes that are otherwise hidden from our view. The first significant attempt to detect solar neutrinos was undertaken by physicist Raymond Davis Jr. in the 1960s. He designed the Homestake experiment, which was located deep underground in a gold mine in South Dakota. The experiment was based on the principle that neutrinos could interact with chlorine atoms, converting them into argon atoms. The process was slow, and the detection relied on counting the number of argon atoms produced over time. Despite the simplicity of the design, the Homestake experiment faced significant challenges. The number of neutrinos detected was far less than what theoretical models predicted, leading to what became known as the solar neutrino problem. This discrepancy between the expected and observed neutrino counts sparked a flurry of research and debate in the scientific community. It raised fundamental questions about our understanding of solar processes and neutrino physics. Some scientists speculated that the issue might be rooted in the solar models themselves, while others considered the possibility that neutrinos might be changing flavors, a phenomenon known as neutrino oscillation. This idea suggested that neutrinos produced in the Sun could change from one type to another as they traveled through space, potentially explaining the lower detection rates. In response to the solar neutrino problem, more advanced detection methods were developed. One of the most notable experiments was the Super Kamiokande, which began operations in Japan in 1996. Unlike the Homestake experiment, Super Kamiokande used water as a detection medium. It relied on the Cherenkov radiation produced when neutrinos interacted with water molecules. This experiment was capable of detecting not only electron neutrinos, but also muon neutrinos and tau neutrinos, providing a more comprehensive understanding of the solar neutrino spectrum. Super Kamiokande's design allowed for the detection of neutrinos with greater sensitivity and accuracy. The sheer size of the detector, which contains over 50,000 tons of ultra-pure water, enabled scientists to observe the faint flashes of light produced by neutrino interactions. The results from Super Kamiokande not only confirmed the existence of neutrinos, but also provided evidence supporting the theory of neutrino oscillation. This was a pivotal moment in our understanding of these particles and their behavior. As research progressed, further advancements in technology led to the development of the Sudbury Neutrino Observatory, or SNO, located in Canada. SNO was designed to measure solar neutrinos using heavy water, which allowed for the detection of all three flavors of neutrinos. This experiment was groundbreaking because it provided definitive evidence for neutrino oscillation. SNO demonstrated that the total number of neutrinos produced in the Sun matched theoretical predictions, but the detection of different flavors confirmed that neutrinos were indeed oscillating as they traveled. The success of these experiments was not merely an academic victory, it had profound implications for our understanding of the Sun and the fundamental laws of physics. The resolution of the solar neutrino problem helped to refine solar models, leading to a more accurate depiction of the processes occurring within the sun's core. It also contributed to the broader field of particle physics, influencing theories related to the Standard Model and beyond. The development of neutrino detection technology has continued to evolve, with new experiments designed to push the boundaries of our understanding even further. Today, researchers are exploring new materials and methods to enhance detection sensitivity and reduce background noise. Innovations in detector design, such as liquid argon and scintillator-based detectors, are being developed to capture even more elusive neutrino interactions. Moreover, the challenges faced in neutrino detection have prompted interdisciplinary collaborations. Physicists, engineers, and computer scientists work together to tackle the complexities of neutrino research. These collaborations have led to the creation of sophisticated software and algorithms that analyze vast amounts of data generated by neutrino detectors. The synergy of expertise from different fields has accelerated progress in understanding not only solar neutrinos, but also neutrinos from other astrophysical sources. In conclusion, the detection of solar neutrinos represents a remarkable achievement that has transformed our understanding of the universe. From the early days of the Homestake experiment to the advanced technologies employed in Super Kamiokande and SNO, each step has brought us closer to unraveling the mysteries of these elusive particles. The journey has not been without its challenges, but the resolution of the solar neutrino problem has opened new avenues of research and deepened our understanding of fundamental physics. As we reflect on the significance of solar neutrinos and the methods used to detect them, we recognize their role as messengers from the sun, providing valuable insights into the processes occurring within our nearest star. The ongoing research in this field promises to unveil even more secrets of the universe, reminding us of the wonders that lie beyond our earthly existence. May this serene journey through the realm of solar neutrinos guide you into a peaceful sleep, where the mysteries of the cosmos continue to unfold in the quiet recesses of your mind. Thank you for joining this exploration of the science behind solar neutrinos. Solar neutrinos serve as vital messengers from the sun, enabling scientists to delve deep into the heart of stellar processes. Understanding their role in astrophysics opens a window to the intricate workings of the universe. As we delve into this exploration, let us first contemplate the significance of solar neutrinos in the context of stellar evolution. The Sun, our closest star, is a dynamic and complex entity undergoing continuous transformation. The core of the Sun, where temperatures reach approximately 15 million degrees Celsius, is the crucible for nuclear fusion. Here, hydrogen atoms collide and fuse to form helium, releasing immense energy in the process. This energy is not merely heat and light. It results in the production of neutrinos, which escape the sun's core almost unimpeded. Solar neutrinos emerge primarily from two fusion processes, the proton-proton chain and the CNO cycle. The proton-proton chain is the dominant process in stars like the Sun, where 4 hydrogen nuclei combine to produce one helium nucleus. This reaction releases energy in the form of gamma rays, positrons, and neutrinos. The neutrinos produced in this process are predominantly electron neutrinos. The CNO cycle, though less prevalent in the Sun, involves carbon, nitrogen, and oxygen as catalysts in the fusion of hydrogen into helium. This cycle also generates neutrinos, albeit in smaller quantities compared to the proton-proton chain. The energy released during these reactions correlates directly with the number of neutrinos produced. As energy flows outward from the Sun's core to its surface, it carries with it the imprint of these elusive particles. This mechanism allows scientists to study the Sun's internal processes through the observation of solar neutrinos. The significance of neutrinos extends beyond their immediate production. They provide a unique avenue for understanding not just the Sun, but also the broader universe. Neutrinos are fascinating not only for their creation, but also for their behavior. One of the remarkable aspects of neutrinos is their oscillation, which refers to the phenomenon where they change from one type to another as they travel through space. This oscillation implies that neutrinos possess mass, albeit a very tiny one. The implications of neutrino oscillation are profound, challenging the traditional understanding of particle physics and prompting a re-evaluation of the standard model. In essence, solar neutrinos are not merely byproducts of nuclear reactions, but crucial components in a larger cosmic narrative. As we transition to the types of solar neutrinos, it is essential to recognize that they exist in three distinct flavors: electron neutrinos, muon neutrinos, and tau neutrinos. These flavors correspond to the three charged leptons in the standard model of particle physics. Each type of neutrino is associated with a specific charged particle: the electron neutrino with the electron, the muon neutrino with the muon, and the tau neutrino with the tau lepton. The difference in mass between these types of neutrinos plays a crucial role in their behavior and interactions. Electron neutrinos are the most abundant type produced in the Sun through the aforementioned fusion processes. However, as they travel through space, they can transform into muon or tau neutrinos, a process governed by the principles of quantum mechanics. This transformation is not merely a curiosity, it has significant implications for our understanding of the universe. The ability of neutrinos to change flavors means that they can evade detection under certain circumstances, leading to complexities in measuring their rates accurately. Detection methods for solar neutrinos have evolved significantly since their first discovery. The historical context of neutrino detection is a testament to human ingenuity and perseverance. The first experiment to detect solar neutrinos was the Homestake experiment, conducted in the late 1960s. Led by physicist Ray Davis, this groundbreaking experiment used a large tank of cleaning fluid buried deep underground. The idea was to capture neutrinos produced by the Sun and observe the resulting interactions. However, the results were puzzling, revealing only about 1/3 of the expected neutrinos. This discrepancy sparked what became known as the solar neutrino problem. As we explore the key experiments that followed, it is essential to highlight the advancements in technology that allowed for more sensitive detection methods. The Super Kamiokande experiment, launched in the late 1990s in Japan, utilized a massive underground water tank equipped with thousands of photomultiplier tubes. This facility could detect the tiny flashes of light generated when a neutrino interacted with water molecules, significantly enhancing the ability to study neutrinos. The results from Super Kamiokande provided compelling evidence for neutrino oscillation, confirming that neutrinos change flavors as they travel. Another landmark experiment was the Sudbury Neutrino Observatory, or SNO, located in Canada. SNO was unique in its ability to detect all three types of neutrinos, providing a more comprehensive understanding of solar neutrino production. The results from SNO helped resolve the solar neutrino problem by demonstrating that the total number of neutrinos produced in the Sun matched theoretical predictions when accounting for oscillation. This resolution had profound implications, not only for solar physics, but also for the field of particle physics as a whole. The challenges faced in detecting solar neutrinos were significant. Scientists had to contend with the fact that neutrinos interact very weakly with matter. This property makes them incredibly difficult to detect, necessitating large and sensitive detection apparatuses. Overcoming these challenges required innovative engineering and a deep understanding of particle physics. As technology advanced, so did our capacity to explore the universe through the lens of neutrino research. The role of solar neutrinos in understanding stellar processes cannot be overstated. They provide a direct glimpse into the inner workings of stars, offering insights into their life cycles and evolutionary paths. By studying solar neutrinos, scientists can glean information about the temperature, density, and composition of the sun's core. This knowledge extends to other stars as well, allowing researchers to draw parallels and make predictions about stellar behavior across the cosmos. Neutrinos serve as messengers, carrying information from the sun's core to the Earth. Their ability to escape the sun without significant interactions means that they arrive here virtually unaltered, providing a snapshot of the conditions within the sun at the time of their formation. This characteristic makes solar neutrinos an invaluable tool for astrophysicists striving to understand stellar evolution. Furthermore, the implications of solar neutrinos extend to the broader context of the universe. The interaction of neutrinos with other particles plays a role in the evolution of cosmic structures. For instance, neutrinos are thought to contribute to the dynamics of supernovae, influencing the processes that lead to the formation of heavy elements. Understanding these interactions can illuminate the origins of elements found throughout the universe, enriching our knowledge of cosmic history. As we reflect on the solar neutrino problem, it is essential to recognize the historical challenges and resolutions that have shaped our understanding of these particles. The initial discrepancies in detection rates led to a re-evaluation of our theories about neutrinos and their properties. The resolution, achieved through the understanding of neutrino oscillation, not only clarified the nature of solar neutrinos, but also opened new avenues of research in particle physics. The impact of the solar neutrino problem on the field of particle physics was profound. It prompted scientists to reconsider the fundamental principles governing neutrinos and their interactions. This re-evaluation has led to a deeper understanding of the universe and its underlying mechanics. The journey to resolve the solar neutrino problem exemplifies the iterative nature of scientific inquiry, where challenges lead to breakthroughs and new questions. Shifting our focus to the broader cosmological significance of neutrinos, we find that they played a crucial role in the early universe. Shortly after the Big Bang, neutrinos were among the first particles to form, contributing to the primordial soup of matter and energy. Their interactions during this period influenced the formation of the universe as we know it today. Neutrinos also interact with dark matter, one of the most enigmatic components of the universe. While dark matter remains largely elusive, theories suggest that neutrinos may play a role in understanding its properties. Investigating the connections between neutrinos and dark matter could yield insights into the fundamental structure of the universe, shedding light on one of the greatest mysteries in modern cosmology.